Mr. the Chairman, I have the pleasure to present to you my talk on the effect of gamma irradiation on morphology and the properties of PLA quasi-30B nanocomposite. This is a collaborative work that was performed in the frame of PhD thesis between our laboratory and the University of Bretagne Sud in France. The intensive use of plastics products in everyday life has created several problems related to the management and accumulation of large quantities of harmful and non-biodegradable plastics waste. And this is characterized by an environmental pollution which represents around 79% of discarded waste plastics, whereas 12% are incinerated. Only 9% of these plastics waste are recycled. In this context, biodegradable polymers are seen as a promising alternative to conventional petrochemical plastics. In fact, there is a great interest towards biopolymers from both academia and industry. And this is shown in figure 2, where we have the world production of bioplastics in 2019 around 1,952 million tons, whereas it is estimated to jump to 2.871 million tons in 2025. Among these bioplastics, PLA is a biodegradable one, and bio-based aliphatic polyester derived from renewable sources such as corn, sugar, potato, and sugar cane. And the PLA life cycle shown in figure 3 indicates clearly that this biopolymer is biodegradable and also biocompostable polymer. Further, it is available at moderate and competitive price while it is produced at industrial scale. Further, PLA has good properties: mechanical, thermal plasticity, and transparency. These makes it as an interesting biopolymer for several applications, including medical, fiber, textiles, packaging, plastics cultivation, construction, paint, cigarette filters, 3D printing, and space exploration parts as shown in figure 4. However, PLA has disadvantages. Some of these drawbacks are inherent: hydrophobicity, brittleness, low gas permeability, low crystallinity. These restrict its extended applications and development. As strategy to overcome these drawbacks, introduction of nanofillers in biodegradable polymers has allowed improving the range of properties and possible uses of these environmental friendly polymers. Therefore, it is expected from the development of PLA clays bionanocomposites an improvement in mechanical strength and stiffness, an increase in thermal stability, the modification of the biodegradation rate, and also an improvement in gas-water vapor properties. On the other hand, degradation of polymer nanocomposites is an extremely important area from scientific and industrial points of view, and a better understanding of degradation mechanism of these materials will ensure the long service life of the products. And particularly, there has been significant interest in the gamma sterilization of polymers being used in some technological fields, such as biomedical and the food packaging, to ensure microbiological safety. However, we know that when exposed to gamma rays, polymers undergo some structural changes. We can have, on one hand, cross-linking, and on the other hand, chain scission, or both phenomena. Briefly, I will show you the materials used. Polylactid PLA from Biomer, and also the quasi-30B from the Southern Clip product as the manufacturer. Here, some processing steps to prepare PLA quasi 30B nanocomposite and also the knit polymer through the use of Brabander to mix in the melting state our nanocomposites with 5% of quasi 30B and the PLA, while compression molding was used to prepare films of an average thickness of 150 micrometers. And the gamma irradiation test was carried out with 60 cobalt industrial equipment at various doses, starting from 20 to 200 kilograms at a dose rate of 1.92 grays per hour under ambient conditions. Let's start discussing now the FTR data. We can see that in figure 6A and the 6B, the knit PLA and the PLA based on the composite before exposure. And these figures are recorded in the carbonyl region. Before exposure to gamma irradiation, we can observe the presence of a large absorption band centered at 1758 centimeters -1, which is assigned to ester groups of the polymer. And we can notice also in figure 7A and also 7B, in the hydroperoxide region, the presence of a large band centered at 3505, which is due to stretching vibrations of hydroxyl groups. After gamma irradiation, we can see that we notice a decrease in the absorption band intensity of the ester groups in both cases, in both samples, with increasing radiation dose. Whereas for the hydroxyl groups, after gamma irradiation, we observe an increase in the band intensity of these groups with increasing radiation dose. However, much higher for PLA C30B nanocomposite. This indicates the occurrence of some chemical reactions and some oxidation reactions. And this is also measured by molecular weight changes. We know that a decrease in molecular weight, as shown in figure 8, in both samples, that is knit PLA and the PLA based nanocomposite, with the radiation dose, expresses the occurrence of transition mechanism. However, the decrease in molecular weight is observed to be more pronounced for knit PLA than PLA based nanocomposite, as indicated by a 74% decrease in molecular weight for the nanocomposite, whereas 80% for the knit PLA. Figure 9 shows the DSC thermograms of knit PLA and PLA based nanocomposite recorded before exposure and after 100 kilograms of exposure. In both cases, it is observed the decrease in the melting temperature from almost 170 to 157. However, we can see that there is a formation of a double melting peak in the case of knit PLA. And this presence of double melting peak in case of knit PLA can be attributed or is caused by the organization during irradiation of the small or the shorter chains and the occurrence of different crystal populations. The main thermal characteristics values of knit PLA and the PLA based nanocomposites are summarized in table 1. And it is clearly observed from table 1 a decrease in melting temperature and glass transition temperature for both samples with increasing the doses. A decrease of the TG is due to the decrease of molecular weight of irradiated samples. However, it is noticed that the decrease is more pronounced for the neat PLA when compared to the PLA-based nanocomposite. On the other case, we notice an increase in crystalline percent with increasing the doses as a result of macromolecular fragments which are able to reorganize themselves. The thermal stability of the samples also was analyzed by TGA, and the table 2 summarizes the main results through the values of T10, T50, and the percent of char recorded at 450 degrees C versus radiation doses. And it is clearly shown that a slight increase of the thermal stability is observed for the PLA nanocomposite sample compared to the neat PLA, which means that the addition of the quasi-30B into PLA provides an enhancement of the thermal stability of PLA nanocomposites. After exposure to gamma irradiation, it is clearly shown that both neat PLA and PLA nanocomposite samples have lower thermal stability with increasing the radiation dose due probably to the formation of low molecular weight spaces. However, due to the nano-dispersion of clay layers, this hinders the penetration of gamma rays and decreases the formation of low molecular weight materials generated by irradiation, and subsequently this can be considered as stabilizing system by the presence of the C30B. And in figure 10 we have a team image of a PLA filled with 5% of quasi-30B, and we can see before exposure to gamma irradiation, and we can see that there is a relatively homogeneous disordered nanostructure and numerous individual clay layers with some C30B layer stacks on the surface. So there is a partial exfoliation of our system. After exposure to 50 and 100 kg, it is clearly observed that the gamma irradiation process induces significant changes in the morphology of PLA-based nanocomposite, and consequently higher level of dispersion is expected with a radiation dose. Finally, the mechanical results obtained by nano-indentation measurements are shown in table 3, and we can see that for neat PLA there is a slight decrease in both modulus and hardness after gamma irradiation, which indicates the occurrence of a reduction in both molecular weight and, weight over age and number over age molecular weight, which can be explained by the polymer chain scission. Whereas it is observed an increase in both modulus and hardness for the PLA-based nanocomposite after exposure to gamma irradiation, and this probably due to the improvement of the nanofiller dispersion, which is consistent with the TEM data. In conclusion, oxidative degradation under gamma irradiation of neat PLA and PLA-based nanocomposite prepared by melt processing causes drastic modifications in the chemical structure, the morphology, the thermal and the mechanical properties. The changes are attributed to the morphology evolution of the irradiated PLA nanocomposite, which is strongly affected by the presence of C30B. Irradiation modifies the steric interactions of clay layers, inducing a better nanodispersion, especially at high irradiation level. As a result, relative ordered structure is formed when irradiation dose increases. Before ending my talk, I would like to thank Dr. Linda Zaidi and Professor Stefan Bruzzo, who contributed to this work.